Okay, today we're putting AI on the witness stand. On the surface, its intelligence looks almost magical, right? But once you start the cross-examination, its story, well, it starts to unravel. We're going to dig into the evidence and ask a really crucial question about what's actually going on inside the machine mind.
And this, right here, is the core of our investigation today. When a large language model solves some super complex problem, is it actually thinking? Is it going through the logic, step by step, the way a person would? Or is it doing something else entirely? Something that just looks an awful lot like reasoning?
So here is the paradox that has researchers so completely fascinated. On one hand, these models can pass some of the toughest exams humans have ever created. They can write intricate code. But then, on the other hand, they get tripped up by the simplest, most ridiculous things. You add a few totally irrelevant words to a math problem, and a model that just aced a PhD-level question can suddenly completely fail. And that's not just a quirk, it's a major clue.
So let's start with our first exhibit. We're going to examine this brilliant, but also incredibly brittle machine mind. We'll see how researchers are basically putting its reasoning on trial to figure out what is really going on under the hood.
The main theory, and this comes from a really fascinating paper from researchers at Apple, is this. It's possible that current LLMs can't do genuine logical reasoning at all. Instead, what they might be are masters of disguise, just performing an incredibly sophisticated form of pattern matching that perfectly mimics the steps of reasoning they've seen in their training data.
Now, to test a theory like that, the old tools just won't cut it. The researchers needed a totally new method, a kind of forensic tool, designed specifically to expose the difference between true understanding and just being a clever mimic.
See, the problem with the standard tests, like the popular GSM-8K for math, is that they're static. It's just a fixed set of questions. This means there's a huge risk of something called data contamination. Basically, the AI might have already seen the exact questions and their answers while it was being trained. It's kind of like giving a student a test they've already memorized. It doesn't prove they can solve a new problem, does it?
So what they did was create a new benchmark called GSM Symbolic. Instead of fixed questions, they made dynamic templates. Now they can swap out names, numbers, all the variables to generate thousands of totally unique versions of the same core problem. This makes it impossible to just memorize the answer. It forces the model to actually grapple with the logic underneath.
And as you might guess, with this new tool, the cracks in the AI's reasoning started to show up, and fast. The evidence they found is pretty mind-blowing, and it really starts to challenge what we think these systems can do.
First up, they tested how sensitive the models were to different kinds of changes. When they only changed superficial stuff, like the names of people in a word problem, performance barely changed at all. But just look at what happens when they only change the numbers. The accuracy takes a much, much bigger hit.
So what does this tell us? Well, it suggests the models aren't using abstract formal logic. They seem to have this strong token bias, meaning the specific numbers and words matter way more than they should. A real reasoner wouldn't care if the problem's about apples or oranges or 10 apples versus 20. But for the AI, these little changes reveal just how fragile its whole process is. Next, they cranked up the complexity. They took a basic problem and made two versions, one simpler, one a little harder. For one model, accuracy on the simple version was great, over 84%, but on the slightly harder version, it just collapses to less than 42%, a huge drop. This shows a really clear pattern. As the chain of reasoning gets just a little bit longer, the AI's ability to get it right doesn't just go down, it falls off a cliff. Every single extra step introduces a new chance for this brittle process to completely break.
Okay, but this is where the investigation gets really interesting. The researchers decided to try something that you or I would find totally trivial. What if they added a piece of information that was completely 100% useless for solving the problem? A classic red herring. The result? It was catastrophic. For some of the best models out there, adding a single useless sentence to a math problem caused their performance to drop by as much as 65%. This one data point is so revealing. It shows the AI isn't telling the difference between what's relevant and what's not. It's just trying to jam every number it sees into the calculation.
And here is a perfect example right from the paper. The problem is asking for the total number of kiwis someone picked. Then it adds this useless detail, but 5 of them were a bit smaller than average. A person instantly knows the size of the kiwis doesn't matter, right? But the models, they see the number 5 and just blindly subtract it from the total, getting the answer completely wrong. It's wild.
So how in the world do we explain all this evidence?
The brittleness, the weird sensitivity to numbers, the total failure to ignore irrelevant facts. Well, a powerful theory has come up that pretty much explains everything we've just seen.
And this comment from an online discussion absolutely nails it. The idea is that the AI isn't using what psychologists call System 2 thinking. You know, that slow, deliberate, logical thought process we use? Instead, it's using System 1, our fast, intuitive, pattern-matching brain, to perfectly mimic the appearance of reasoning steps that it saw millions of times in its training.
This whole process is called probabilistic pattern matching. The AI isn't really understanding a concept like addition. It's just calculating the most statistically likely sequence of words and numbers to spit out next based on billions of examples it's seen. It's a performance, not a real computation.
The Rubik's Cube analogy is honestly perfect for this. The very first time you solve one, you're using slow, careful reasoning for every single move. But after you've done it 1,000 times, you're not reasoning anymore. It's just muscle memory, an intuitive, lightning-fast pattern. The AI has basically done the equivalent of solving 1 billion Rubik's Cubes, and now it can only operate on that intuitive, pattern-matching level.
And look, this limitation isn't just about getting math problems wrong. This could represent a fundamental roadblock on the path to the ultimate goal of AI research, artificial general intelligence, or AGI.
Now, you might be thinking about that common trick to improve AI reasoning, the chain of thought prompt, where you basically just tell the model to think step by step. For a while, that seemed like a pretty good workaround, but is it a real fix?
Well, not so much anymore. According to new research from Wharton, that technique is getting less and less effective. For the newest generation of reasoning-focused models, telling them to think step by step gives you almost no benefit, while still costing you more time and more compute power. So it seems like you can't just prompt your way out of such a fundamental limitation.
Ultimately, we're smashing into these deep, almost philosophical roadblocks. You've got the symbol grounding problem. The model doesn't know what a kiwi actually is in the real world. It lacks a world model. It has no internal understanding of physics or cause and effect. And we're seeing that just scaling up, throwing more data and more computers at it, isn't leading to true understanding anymore. These are the huge hurdles that pure pattern matching may never be able to clear.
Which leaves us with the final big question. We've built something that's a brilliant mimic, an actor that can play the part of a reasoner almost perfectly. But if that's all it is, what's the next move? What will it actually take to build an AI that doesn't just mimic understanding, but finally achieves it?